Apron from Bangladesh.
Yes, Professor.
You are there, okay. And Yaqub Safwan from Bahrain.
Yes, I'm there.
Okay, good. So all of you are here. Good. So I can start then. Okay. And you all have the lecture notes. You received the lecture notes, right?
We have received the lecture notes from the email you have sent to Professor.
Okay, good. Okay, so what I'll be teaching you is about the group theory. So read groups. I mean group theory. Can you read my handwriting? My handwriting, or should I write bigger? Should I write bigger than this, or can you?
It's clear enough for me. I don't know about the others.
I think someone, yeah.
I can read it.
One of you said that they cannot read, right? Okay. So anyway, so let me see. So if one of you can, I mean, any of you cannot read, please let me know.
Professor.
Huh?
Professor, can you hear me?
Yeah, I can hear.
So Bakhtash was saying that he can see the notes, the blackboard. And I think we should just tell him that there is at the right, just at the top, there is a view, something it says view, and he has to just select their full screen so that he can see the board is like, I mean, on the screen. So he can see, he can watch all the full screen. Can you hear us?
Yes, now full screen. Thank you very much. No problem. Yeah,
okay. Okay. Thank you. Thank you, Professor.
So, I mean, you will see that the group theory plays a very important role in particle physics. In several courses that you'll be following later, standard model in particular, will use extensively the knowledge of group theory. Okay, so the purpose of this course will be to, so that you can learn these things, and it will be easier for you to follow the next courses. Okay, so first of all. So in particular, let me just say what kinds of groups. You're already familiar with some of the groups, right? You must have, maybe you have not seen it in a very formal way, but you already know certain symmetries in the physical systems, right? For example, you know there's a translational symmetry. Right? So if you translate the whole system, the physical laws do not change, right? So this is translational symmetry, also rotational symmetry. Again, you have seen this rotational symmetry in several problems in physics. In particular, for example, the hydrogen atom problem in quantum mechanics. When you try to solve the hydrogen atom, you had to use a rotational symmetry, crucial, right? Because the force is depends only on the radial distance between two charges. Therefore, the system is rotationally symmetric. So that, and indeed, these symmetries play a very important role because these are intimately connected with the conservation laws. Okay. For example, translational symmetry is responsible for momentum conservation. And rotational symmetry is responsible for angular momentum. Conservation. So these symmetries also play a very important role in the conservation, in the property, physical properties of the system, right? We will see in part of this course, okay, these two symmetries have symmetries which act on the space, right? In fact, in the RQM, in the relativistic quantum mechanics that Eddie is teaching you, you will see a generalization of this rotational symmetry and translational symmetry into what is called the Poincare, or first of all, let me call it Lorentz symmetry. This you will study. Probably some of you have already seen this, but it's a generalization of rotational symmetry where you include also time, right? Space and time. And this Lorentz symmetry is basically like a rotation between the space and time. Okay, you can think of it as some kind of a rotation. So this you will study again. But in particle physics, as you will see later in the other courses, there are several other symmetries which are generally called as internal symmetries. Okay. Now these are, you see, these are all related to the space and time. But then there are some internal symmetries which give rise to various charges, various types of charges to the particles, to the fundamental particles. Okay. So our goal will be mainly to discuss group theory, keeping this in mind, this last aspect in mind. In RQN, you will study Lorentz symmetries in detail, Lorentz symmetry, and when you put together the translation symmetry and the Lorentz symmetry, you get something called Poincare symmetry. Okay. So in RQN, you will study in more detail here this Lorentz symmetry and Poincare symmetry. But so my focus mostly will be to develop the tools which will help you to understand particle field exposures. Okay. So that's the main idea. Okay. Any comment or question up to this point? No. Okay. So then I can just erase this and start the course. Okay, so first of all, let me start defining what is a group theory. What is group? So definition. And then I will give some simple examples to begin with. And then as the course proceeds, we will study more and more complicated examples, okay, which are essential for particle physics. But I'll start with the very simple examples. So what's the definition? So first of all, so a group, which I will usually always denote by capital G, okay? Group, capital letters, G or H or whatever. So I'll use that as a notation. So first of all, the group G is a set of elements. Okay. So for example, let me just call it G1, G2. So the small letters will denote the elements in the set. So capital will be the whole set, capital letter will be the whole set, and the small letters will be the elements of the set. So I'm just calling it G1, G2, and so on and so forth. Okay, this set could be a finite set, or it could be an infinite set. It could be an uncountable set, you know, for example, the set of all real numbers. So this is just a schematic way of writing it at the moment. This need not be finite or even countable. Okay. But this is not just a set. I mean, otherwise, of course, if it is a set, there's nothing special about the group, right? So what's the most important thing about the group G is that there exists a composition rule or product rule. Or sometimes, or generally people call it as a product rule, which I will denote by a small circle. So this is the notion of that. This is the notation for this composition rule. So what does this rule say? Take any pair of elements in the set, let's say G1 and G2, for example. Then this composition rule, so given these two elements, what it does is this composition rule gives you again an element of the set. Okay. So it will be, say, this could be, let's say, something. So this belongs to this original set G. Okay. For arbitrary, for all G1 and G2 belonging to the original set G, this composition rule associates, for every pair of elements, it associates a third element in the group G. This composition rule is the most important part of the group. But this composition rule has to satisfy certain conditions. So these conditions, now let me just list the conditions. You can see this part of the blackboard, all this part. So is that?
Yes.
You can see, good. Okay, so first of all, so this is this first property was this. This is called closure property. Closure. Okay. That is the product of these two elements, G1 and G2, is again inside the group G. And this should be true for all G1 and G2. That's a closure property. So it just says that under this composition rule, this group is closed. This set is closed. Okay, that's the first property. So let me just write it as 1. The second thing is the associativity. That this composition rule should be associative. Associative. So what does it mean? So now let's say I have three elements, G1, G2, and G3. Take arbitrary 3 elements inside the set. Okay. Now you can take, let's say first I take G2 times G3, G2 product G3, and then, okay, this is some element of G. And then I take the product of this element, G1, with this element in this order. So first I take the product of G2 with G3, okay, which will be some element of G. Then I take the product of G1 with that element. Okay, this will be again some element in the G, because we already assume that this composition rule is satisfies a closure property, right? But then you could have done in another way. You could have first taken the product of G1 with G2, okay, which is again an element of G, and then take the product of this element with G3. So there are these two different ways of taking the product. A priori, it is not obvious that these two should be equal. Both are elements of the G, but it's not obvious that they should be equal. Well, this is the property of associativity. So what we are saying is that if you call this set and this composition rule as a group, then it must satisfy this property, that it's associative. Okay? So this is if this is satisfied, then you can say that the composition is associative. This product rule is associative. So this is one thing. I should mention here that you see the order of this, when I say, for example, G1 times G2, you have to keep order in mind. It is not necessary that G2 times G1 is equal to G1 times G2. This may or may not be. Okay? In some cases, it may be that G1 times G2 is equal to G2 times G1, right? But in general, it need not be. Okay? So keeping the order is very, very important. Okay? You know, for example, you must have done the matrix multiplications, right? In your undergraduate course. So matrix multiplication is not doesn't commute. Ordering is important, right? So you have to keep the order in mind. I mean, you have to be careful about the order. If it happens that this is equal to that for all G1 and G2, then it's a special type of group. That group is called abelian group. Okay, but in general, that doesn't happen. So the ordering is important. So ordering is important. So these are the properties of the compositions, but there are still a few more conditions. Unfortunately, I have to erase this now. Huh? But you have it in the notes in front of you. If you have the notes, you can see that. The third property is that there's a special element in G. So the third property is that there exists an element which we will call this element as, okay, I will keep following the notation. I will call this element E, okay, inside G, which is called identity, where this E is called identity. Okay. So what is the property that this E has? The property is that for all G belonging to capital G, for every element of the capital G, G composition E, G product E, is the same as E product G, is equal to G itself. Okay. So this is the, so you see it's like identity, right? Because it doesn't do anything. E times G is again G, or G times E is again G. Right? So what E does is that it takes any arbitrary element of G and gives you back again the same element. So it's an identity. So that's what it's called. That's why it's called identity. And finally, the fourth property is that for every G belonging to capital G, there exists an element, an inverse element. Inverse element. Which is denoted by, called G inverse. This is a notation, G inverse. And what the property it satisfies is that G inverse times G is equal to G times G inverse is equal to identity. Okay. So these are that's a property. So it's an inverse in the sense that you see the composition of this element with that element gives you the identity. And again, the order doesn't matter for this. Okay. So any question on that? Let's just pause a bit. You have any questions on this? Because it's important to understand this, the basic definition of the group G. I'll now, after this, I will start giving some examples. So it will probably become clearer by looking at the examples. But up to this point, is there anything which is not clear? Okay. And as I mentioned before, in general, I mentioned that you have to keep track of the ordering. I mean, G1 times G2 is not necessarily G2 times G1. But if it happens that for arbitrary two elements of the group, the G1 times G2 is the same as G2 times G1, then you call that group an abelian group. Okay, just a terminology. You call, so every element commutes with another element. Commutes meaning ordering doesn't change. Okay, in that case, you call that group abelian group. Otherwise, you call the group non-abelian. Right. So let me just mention, this was the main definitions, but now I just mentioned the case where if it happens that for all G1 and G2 belonging to G1 times G2 is equal to G2 times G1. Many times I just use the word times instead of saying product, but meaning is the same. I mean the product, this product rule. If it happens that this is equal to that, then you say that this group is abelian. Then G is called an abelian. It's called abelian. So it's a special type of group, abelian group. If it is not the case, if this doesn't happen, then you say the group is non-abelian. It is not abelian, non-abelian. Okay. So this is a basic definition. Now let me just start giving some examples, which will probably clarify the definitions a bit more. Is that okay? Now, I mean, if there's any question, please ask me. You should ask as many questions as you can.
Yes, I have a question, Professor. So the abelian group, all of the elements inside the group have to be commute so that I can call it an abelian?
Yeah. So this should be true for all elements. Take any two elements, and if this is satisfied, then you call the group abelian. Because you see, already, I mean, this happens for this, right? E with any G, it commutes, right? Ordering doesn't matter. And G with G inverse, also the ordering doesn't matter. So this happens for all the groups. But what we are saying here is much stronger than that. Not just for, I mean, here it's not arbitrary elements, right? We have chosen one of them to be the identity element, which is a unique element. There's only one such element in the group. So when you take one of them to be identity and other to be any element, then it commutes. But that doesn't mean that if you just take two arbitrary elements, that they will commute. So for abelian, it's a very strong condition. It's not just for this pair or that pair. It should commute. It should commute for every pair of elements. Okay. I mean, in fact, so now when we look at examples, the initial examples, probably the first 2-3 lectures, I'll be discussing abelian groups, maybe the first couple of lectures. But very soon we'll move to the non-abelian groups, because that is what is really more interesting for particle physics. Okay. Okay, so so most of the course will be on the non-abelian group. All right. Any other questions? Okay. Then let's move to some examples. So the first example is the, so let's just consider, so we'll start with some examples of finite groups. Although in the course, we'll be entirely focused on not finite groups, groups which have infinite number of elements. But this is just to start with. So consider this set, which I call Zn, okay? Where n just denotes how many elements are in the group. And let's consider the following set: 1 omega squared up to omega to the n minus 1, where omega is e to the power of 2 pi I over n. Okay. E to the power of 2 pi I over n. So you see, so why we stopped at omega to the n minus 1? Because if I had taken omega to the n clearly is equal to 1. Right? Because that's the same as e to the 2 pi I, which is equal to 1. Okay. So when you take omega to the n, but that's exactly that element, right? So that's why this set stops at this. The number of elements is simply n. Now, what is the, so this is the set. At the moment, it's a set. What is the composition law? What is the product rule? Well, let's take the product rule to be the ordinary multiplication of complex numbers. Ordinary multiplication between two complex numbers. Complex numbers. So, I take any arbitrary set, element of the set, let's say omega to the r and omega to the s, right? Where r and s are between, where r and s are between 0 and n minus 1. I mean, when omega to the 0 is just the 1. Right? Okay, so take the so we said composition law is nothing else but the ordinary product of these two. Well, what is ordinary product? This is e to the 2 pi I over r times r over n. That is this one, and times e to the power of 2 pi I s over n. Well, if the faces just, when you take the product of these two faces just add up, right? So this would be e to the power of 2 pi I r plus s over s, which is the same as omega to the power of r plus s. Okay. So, of course, when you say r plus s, you have to remember that if R plus S happens to be bigger than N, then you use again this property that omega to the N is 1. Okay. So for example, suppose R plus S happen to be N plus 2 or N plus 1. Okay. Then this is the same as omega. So this is the same as omega to the N plus 1 would be the same as omega. Okay. So it will be again one of the elements here. So you see this product rule has again given you back one of the elements inside the set. Right? Is that clear? So therefore, this composition rule satisfies the closure property. You see, product of any two elements here is again a third element. Is again one of the elements here, right? So closure is satisfied. So let's just write down. So the closure is satisfied. So first property, closure, is okay. That's satisfied. Now, the second property was the associativity. Associativity is obvious because this is just, we said, is ordinary multiplication. It's just the usual multiplication. So the usual multiplication of numbers always is associative. So the associativity is just trivially satisfied. Then look at the identity. So what is identity? So what we call E, well, identity should satisfy that E times any element should give you back the same element, right? But that is clearly, what is that? This E is nothing else but the 1, the element 1 here. Because 1 times any quantity, because product is just usual multiplication, is going to give you back the same number, right? So 1 times, so if I take 1 times omega to the R, it gives you back omega to the R because this is just the ordinary multiplication. Okay. And what is the inverse? So what is the, if I take omega to the R, and what is the inverse of that? Well, that's nothing else but omega to the power of minus R. Okay. But that doesn't look like it is inside the set, but it is, because I can rewrite this as omega to the power of N minus R. Right? Because omega to the N is simply 1. So N minus R is again, will be one of these elements. So you see that the inverse, so the inverse also exists within this set. And of course, you can see that omega to the N minus R times omega to the R is the same as, because it's the usual multiplication, it's the same as omega to the N, which is equal to 1, which is the identity. So it satisfies that. So all these properties are satisfied. But however, this group is abelian, you see, because the ordinary multiplication is abelian. When you take two numbers and you use the ordinary multiplication rule, it doesn't matter, the ordering doesn't matter. So this is an example, this example is an abelian. So it's a finite, it's a finite finite group of the total number of elements is n, and it's an abelian group. Okay, this one example. Now, yeah, any question on this?
Yes, Professor. Is there a minimum number for the? Is there a minimum for a number of elements in any group?
Is there a minimum?
A restriction for the number of elements in any group in the definition?
No. There's no restriction.
So we can say that any group that has only 2 elements is an abelian group?
If you have only 2 elements,
Is that
yeah, that will be, because there's one of them is identity and one of them has to be identity, and the other element is whatever the element is, then the ordering doesn't matter. So it's abelian, right? Because one of them is, so there are, if you say there are only 2 elements, then we call it E and something G. Okay. This is the set of 2 elements, right? But E is, identity must exist. So it's that. So I call that as identity. Then E times G is the same as G times E. Of course, G times G is obviously G times G, because of nothing. So the whole thing is equivalent for two elements. Now this was n elements which are. Okay, now let's go to this non-equivalent. Yeah, sorry.
Yeah, I have a question. If the group is already abelian and I want to construct a subgroup, so will the subgroup will be also abelian, or?
I mean, I have not defined a subgroup yet, but okay, just to anticipate, I mean, I will later on define more precisely. But what the subgroup of a group is, first of all, it's a subset of the original group. Okay, and but the most important thing is that, I mean, subgroup. When you say subgroup, it's also a group, right? So it must also have a composition rule. Okay, but this composition rule must be the same composition rule that was already defined in the original group. Otherwise, it's not called a subgroup. But since the original composition rule was abelian, was commuting, therefore the subgroup will also be commuting.
Okay.
Yeah. Right. Now let's look at a slightly more complicated group, which is again a finite group. Okay, so this is what is called a permutation group. The permutation group, permutation group of n elements, which is usually denoted by Sn. This is the Sn is the permutation group, and what it does is that if you write down say n elements. So let me define what it does. So I start with the n elements, let's say x1, x2, up to xn, n elements. Then what this group does, it's change now what you do is that you look at all possible orderings of this n elements. So here I have ordered in one group. So first one is x1, second one is x2, third is x3, and so on and so forth, right? But I could have chosen another ordering. For example, I could have chosen x2, x1, and keep everything else the same. Okay. Or in general, so what I'm saying is that this group Sn is just the permutations of all of these n elements. Okay. So here Sn is so an arbitrary element of Sn. This consists of all the set. What is the set? It is all permutations. All permutations of n elements. N elements. Let's just to take some examples. Let's suppose n is equal to 2. Well, this is S2. Well, in this case, I start with the two elements, x1 and x2. Now, the only permutation you can think about is, first of all, so no permutation. I mean, just identity element doesn't do anything. Okay, so one of them is identity element, which just takes x1, x2 to again x1, x2. It didn't do anything. And the other element that you can think of is again is the x1, x2 goes to x2, x1. These are the only two possibilities. Okay. So this element is identity because it didn't do anything. And the other element, let's see what the, so yeah, this here I will use the same notation as is written here. This element I will call G12. Okay. So what is G12? The reason for this notation is that by looking at it, you know exactly what it is doing. It is just exchanging the first and second positions. Okay. So G12 means just exchange the first position and the second position. So what was in the first place has moved to the second place, and what was the second place has moved to the first place. That's what this G12 does. So this element S2 consists of just two elements. This set has only two elements, E and G12. And you can immediately see what it does. First of all, E is identity, because you can. So what is the composition rule? Composition rule is just do, so for example, yeah, maybe I should have already defined here. So, I mean, I have this permutation elements, right? It will have all, I mean, let's call these elements, I don't know. Okay, there will be identity element, of course, always. Identity element is always of some, which doesn't change the order at all. It just keeps it as it is. It doesn't do anything. But then there'll be lots of elements here. For example, you'll have G1, 2, pairwise G2, 3, so on and so forth. Or you can have even moving the 3 positions simultaneously, 1, 2, 3, etc. A lot of elements are there, right? And so what is the composition rule of this? Composition rule is just in the definition itself, because if I say what is G12 times G13? So the question is, what is this, right? Well, G13, or G13, what it does, it exchanges the first and the third. Okay. But after that, when you apply G12, what the G12 will do, it will just exchange these two things. So the composition of this is simply by action, successive action. Okay, is that point clear? Because I'm not separately defining the composition rule. All I'm saying that the set of all the permutations. So what you do, the way the composition rule is defined here is simply by the action on this n tuple. Right? So first take some element, do the permutation with that element. Okay. Then you take another permutation element and again do the permutation on the result of the first operation. Okay. That's how you define the composition rules here. Maybe I will. Okay. So let's look at this particular thing first of all. Then I will go to the n equal to 3, where we'll work out the details a bit more carefully. So here I have these two elements. So first, suppose I look at the E times E. So what does it mean? I apply first the E on this, and on the result, again, I apply E. Nothing happens, of course, it is the same, right? So this is again E. What if I take E times G12? Okay. So the rule that we are working is that the thing which is on the rightmost part, that acts first. Okay. Then as you come, then the next one applies is after. Right? So this is some ordering I've given here. So what it will do? So let's just do step by step. First of all, so I'm asking the question, what this guy does, what this composition does to the x1, x2. First, let me apply G12. So I still have to apply E. So I remember that. Do I keep the E there? First, I apply G12. It gives you x2, x1. Right? Because G12 acting on x1, x2 is nothing else but x2, x1. Okay. Now I apply E on this resulting, on this result. But E doesn't do anything, right? So this gives you back again x2, x1. But that was the same as G12 acting on x1, x2. Right? Because this is the same as G12 acting on x1, x2. So from this, you conclude that E times G12 is the same as G12. Yeah. Because you see, this is acting on x1, x2, and that's acting on x1, x2, and the two are equal. So you say E times G. So E times G1, G2 is equal to. So E times G1, G2 is equal to G1. Now, what happens if I first apply E and then apply G12? Again, it's the same, right? So the next one I apply, look at here. First I apply E and then G12. Well, that's even easier than that on the first one, because again you do the same thing. E acting on that just gives you x1, x2 itself. And then this gives you x2, x1. I mean, this already directly. So G12 times E is nothing else but G. Okay. So that is the third one. So from this we conclude G12 times E. And finally, let us do G12 times G12. Again, to understand what the composition means, I have to apply on x1, x2. Okay. The first action on that exchanges the two. Okay. So this gives you, I mean, this is still, I have not applied this, I'm just applied the first one. So this, so G12 acting on x2, x1. Correct? So what I have written here, I keep that outside and look at first how this acts on this. And this acting on that is simply x2, x1. And on the result, I have to apply G12. And what is that? So I have to again exchange the first two positions, but that brings you back x1, x2. Okay. Which is the same as E acting on x1, x2. Okay. So conclusion is G12 times G12 is E. Right? So we have obtained all the product rule, all the composition rules we have obtained from this definition. So the composition rules were, let's say I can write it as E, G12, E, G12. I'm just writing a product table. So what this means is that you take, so here E times E is E, G12 times E is G12, E times G12 is G12, and G12 times G12 is E. So this is the product rule. This gives you this table. This table gives you the composition for the. You see, I want you to appreciate the difference between the first example and the second example. In the first example, we directly define the composition rule as product. Huh? In the second example, we have not defined directly the composition rule. Instead, what we did was we defined this set as some operations on two elements, x1, x2, two ordered elements. And that definition itself gives you what is a composition rule. So we have deduced the composition rules from that. Okay. So this is a more indirect way of defining the composition rule. But at the end, this is the composition rule. Okay. And notice that this group is again a abelian group. Okay. Right, because you see the E times E is E. E times G12 is the same as G12 times E. Okay, and G12 times G12 is, of course, it gives you back E. So now this group is actually, this composition rule is exactly the same as the composition rule for Z2. Right? Z2, we had defined Zn, the first example. That example, if we specialize to n equal to 2, n equal to 2 means the set includes only two elements, 1 and e to the power of 2 pi I by 2, but that is the same as e to the I pi, which is minus 1. Okay. Now look at the composition rule. This is the identity, and think of, suppose I just give it, think of G12. The composition rule of Z2 is the same as that, because for Z2, you see, this times this is, of course, itself. This is the identity. This times that gives you back that, because this is the identity, which is the case here. E times G12 is G12, or G12 times E is G12. Okay, and finally, G12 times G12 is identity, but that's exactly the case for the Z2 also. Minus 1 times minus 1 is plus 1. Okay, so in this particular case, Z2 is the same as S2. So what we concluded, this is the same as S2. S2 was the permutation. But that's just a special case. That happens only for n equal to 2. It doesn't happen for bigger n. It's an accident. Okay, any question on this? Because now I'll go to the S3. S3 is a bit more complicated. So I will do the S3 example. Okay. Any question? No? Okay. So then let me give the example of the S3. So S3 will be, of course, then I have to start with the 3 elements, X1, X2, and X3. And then S3 is nothing else but all the possible permutations, right? So first of all, you ask the question, how many elements are there? Well, the elements are, first of all, the identity, okay, which doesn't do anything, it just keeps the ordering the same. Then I can have pairwise permutation, okay, just a pair. So I can have G12, or I can have G23, or I can have G12, right? But this is pairwise, you know, pairwise. You can also do the permutation all the 3 simultaneously, right? So for example, I can move X1 to X2, X2 to X3, X3 to X1 simultaneously, right? At one go. I mean, these were just, G12 didn't do anything to that. It just exchanged these 2. Similarly, G23 didn't do anything to that. It just exchanged these 2, right? But you can also think of permuting in a way that, say, X1 goes to X2, X2 goes to X3, X3 goes to X1. I mean, these positions. No? So this will be denoted by G123. In fact, let me use the same notation because this is a matter of a bit of a notation here. So what G123 and G132. So what this notation is saying is, so let's say G123 acting on, so G123, I have just defined explicitly what it does. It acts on X1, X2, X3, and it permutes to, so the first, so what this means is the first position goes to the second position. Second position goes to the third position. And third position goes to the first position. That is the meaning of this notation. So first one, so this goes to, X1 goes to here, X2 goes there, and X3 comes here. On the other hand, what does G132 do? X1, X2, X3. Well, the first guy goes to the third position. So X1 goes to the third position. Third guy goes to the second position. So X3 comes here. And finally, the second guy goes to the first position. You see, these 2 are not the same. Okay? So this is like thinking of, one is like rotating this way, one is going, cyclically moving it along this way. Other one is cyclically moving that way, right? I mean, if you, instead of writing it like this, if you had written in a kind of arranging in a cycle, let's say X1, X2, and X3, then one of these guys is doing a counterclockwise rotation. I mean, this point goes there, that point goes here, this point goes there, right? This one, on the other hand, does the clockwise rotation. X2 goes to X1, X1 goes to X3, X3 goes to X2. No? So these are two different elements of the permutation. This is all. These are the, for S3, these are the only 6 permutation elements. Okay. And you can try to, okay, try to check. Try to see whether this is all you have, or is there anything else that we have missed out. Try to check that. But this is all. In general, the number of elements in the permutation group Sn is equal to factorial n. Okay. that is the number of number of possible permutations of n elements, is a huge number, is factorial n. So for example, for n equal to 3, factorial 3 is nothing else but 6. And indeed, you see that is a 6. Okay. For n equal to 2, factorial 2 is 2. And that's what we found for S2. S2 had only 2 elements, right? Identity and G12, because there are only 2 things. But the number of elements grow very, very fast as you increase the n, it grows very rapidly. It's a factorial growth, so it's a huge. Okay, but now let's ask the question. Remember, for S2, we found that that group was abelian. Okay, can we say something about S3? Is the S3 abelian or not? So you can see, so the composition rule, actually this is an exercise. This is an exercise problem. You should try that exercise 2.1, which says that G23 with G12 is G132. On the other hand, G12 times G23 is G123. So you see that this is please try to work it out. Okay, try to see. It's not difficult. Right? I mean, just successively start applying. So, for example, this. Okay, let me just try to just do one part. So, what does it do? So, let's see. I take G23 and G12 and apply this on X1, X2, X3. Okay. So, what do I get? What is the rule? So, you start from the rightmost part and first do apply that, and then on the result you apply the next one, right? That's a composition rule. So first apply that. So what do I get here? G12 acting on this just exchanges 1 and 2. So X2, X1, and X3. Okay. Then I apply G23 on this. So what it does, so what was that? 3, 2. So 2, 3 exchange, right? So I exchange these two. Now, this means second position and the third position. So this gives you X2, X2, X3, X1. Okay. Which is G132, which is G132. Okay. So remember, it's so what it's doing. I mean, when I think this is a matter of definition, but the way we are using this definition is that this means whatever is in the second position and the third position, they're exchanged. Okay, that's what it means. So therefore, I exchange X3 with X1. I mean, these two elements I exchange, so you get that, and that was nothing else but what we said is the G132, because G132 acting on X123 is exactly that. Okay? So this is the way you prove that. But then you should check also that this is true, that G12 times G23 is G123, but these two are not the same. Huh? So you see here, what is the difference between this? The ordering has changed, right? It is G23 times G12, this is G12 times G23. So we conclude that G12 times G23 is not the same as G23 times G12. So this group is not abelian. If it was abelian, this should have been equal, no? So it's not abelian. Okay. Now, any question on this? Now, because now I'll start moving to the infinite number of groups with infinite number of elements. But any question? I mean, these are just examples I'm giving. As I said, we will not be really discussing finite groups. We'll be always talking about continuous groups. I mean, infinite number of elements. Actually, more than infinite, uncountable infinity. So, but these are just some examples to straighten the definition of the group. So you see how the definitions of the group is working here. You should check, in this example, you should check what are the inverses of each of these elements. This is of course identity, but then identity exists. But you should also need to prove, you should check that, because if it is a group, first of all, the closure property should be checked, associativity property should be checked, okay? And you have to also show that every element has an inverse. Okay. So you could try to check all of these things. It's a good exercise too, because then I think you get more comfortable with this, the definition of the group, all the properties that group should satisfy. No? Okay. So now let me go to an example of infinite number of elements. So first of all, yeah, so let's consider the group of all integers, the set of all integers, the group G, which is denoted by Z, just Z, no n here, there's no index n here. Zn would mean there are only n elements, right? 1 omega up to omega to the n minus 1. But now I don't have any index here. And this is nothing else, the set of all integers. Set of all integers. Okay. With what is you have to also specify the composition rule. It's important to, because the group is not just a set. It comes with the composition rule. So what is the composition rule? Just the so composition rule is just the ordinary addition. Addition of two numbers. Well, it's immediately obvious that all the group properties are satisfied. Well, let's see. Under addition, if I take the addition of two integers, again you will get back an integer, right? So closure property is satisfied. Of course, this addition is also commutative, right? It's abelian. It doesn't matter in which order you add the two numbers. Addition is commuting, so it's abelian. It's associative, clearly. Additions are all, this is just ordinary addition that you are familiar with, right? So it is, so it's closure is satisfied. The associativity is okay. This actually, yeah. What about the identity element? Identity element is just a zero. Because the set of all integers also includes a zero, right? Because 0 plus the composition is nothing else but the ordinary addition. So 0 plus any integer n is again n. No? So the identity is a zero element. And what is the inverse? Inverse of say n is nothing else but minus n. Why? Because n minus n equal to minus n plus n equal to 0. 0 is identity. So all the group properties are satisfied here. It's a abelian group. Okay. This is, it should be, one should see that, you see, you cannot, I mean, for this composition rule, you could not have used multiplication, ordinary multiplication. Ordinary multiplication wouldn't make sense. Why? Because if I take, instead of ordinary addition, if this composition rule was equal to the ordinary product, ordinary multiplication between two numbers, multiplication, then it cannot be a group. Why? Because what is the inverse of n? Well, inverse of n, ordinary multiplication would mean inverse of n should be 1 over n, right? But 1 over n is not necessarily an integer. I mean, it's an integer only for n equal to 1 or minus 1, right? For anything else, it's not an integer. So this, even the inverse will not exist within this set, right? So this is not a group. I mean, it will not be a group if you had used, for the composition law ordinary multiplication. It's not. That was the thing here. Okay. Now, so this was a discrete group. Yeah. I mean, this is a kind of it's infinite, but it's countable infinity. This number of elements is infinite, but it's countable infinity because you can enumerate all these elements, right? So integers. So it's countable infinity. Now let's look at a continuous group. So continuous group, one example here is consider the set. So the set is the set of all positive real numbers. Positive, so greater than 0. So all the numbers are greater than 0. All real numbers. The set of all the real numbers is actually uncountable infinity, right? You cannot enumerate. It's a much worse infinite than that. So a set of all positive real numbers. And what is the composition rule? So the composition rule, omega, the dot composition rule is ordinary multiplication. Is the ordinary multiplication of two numbers. So let's see if it satisfies all the properties of the group. Closure property. If I take two real numbers, two positive real numbers, product of that's going to be again a positive real number, right? Because ordinary multiplication of two positive real numbers will again be a positive real number, right? Because all the numbers are greater than 0. When you take the product, it's again going to be some number greater than 0. So closure is satisfied. It's of course abelian, commuting. So it's an abelian group because ordinary multiplication is commutes. Associative also because ordinary product is again associative. What about the identity and the inverse? These are the two things to check. Identity is nothing else. Identity element is simply the 1, the number 1. Number 1 is included in the set because we have any real number greater than 0. That's the set. So 1 is also the thing. That's identity. That's clear because 1 times any number is again back again to the same number, right? So that satisfies the property of identity. And what about the inverse? So inverse of any real number, let's say x. So x is some number greater than 0, real number. Then inverse of that is simply 1 over x, which is again clearly a real number greater than 0. So this is the inverse. So the inverse of x is equal to 1 over x. Why? Because x times 1 over x is identity. Okay. So this is okay, sorry, the example given here was different from the example I gave here. Okay, this is an example. The example given in the notes was actually the set of all real numbers, positive and negative, with the composition rule being addition. Okay, that will be also another example. So just take this example, but instead of taking set of all integers, take set of all real numbers. Okay. You can immediately see that will also satisfy all these conditions, with the ordinary addition being the composition rule. But this was another example which is not appearing here, but I think it will probably appear later on, maybe in the next chapter. But anyway, so this is another example. So this group G is usually denoted by R plus, which means set of all positive real numbers. R stands for real numbers. real R, and plus just indicates that it's all positive, I mean greater than 0. So this is a group with the composition rule being multiplication. On the other hand, if you had taken the group R, just R, not R plus, this is a set of all real numbers. Then you cannot use the composition rule as a product rule. You cannot, but you can use ordinary addition as a composition rule. And it will have again the same, all these properties will be the same for, the inverse of any real number x will be minus x. Okay, identity is the 0 element, because 0 plus any x is x. So all that goes through. But you see, you could not use the multiplication. Why? Can someone say why? Can any of you answer this question? Why you could not have taken the set of all real numbers and use the multiplication as the composition rule?
Because of the 0?
Exactly. Because the inverse of 0 is infinity, right? So inverse of 0 does not exist for that reason. But addition is perfectly fine. Here, you see, precisely for this reason, we removed the 0. You see, we are restricting to only positive numbers. So of course, in this case, the inverse exists, 1 over x. Since x is finite, x is not 0, 1 over x is also not 0. So not infinity, 1 over x is not infinity. So it makes sense. And finally, now let's look at another example, which is going to be the kind of the groups we'll be studying in the later part of the course. So this is the most simplest possible group of the types that we'll be studying later. Let's okay. So this group is called U1 group. U1 group. So what is the set? The set is e to the elements of the type e to the I theta, where theta is between 0 and 2 pi. So it's again continuous. You see, theta changes continuously from between 0 and 2 pi. There's parameter space between 0 and 2 pi. Why up to only 2 pi? Because e to the 2 pi I is the same as e to the 0 I, right? So 2 pi will be the same as 0. Because e to the, if I take theta equal to 2 pi, that's the same as taking theta, this is the same as taking theta equal to 0. So that's why this is going from 0 to 2 pi. And what is the composition rule? The composition rule is just ordinary multiplication. It's just the ordinary multiplication of complex numbers. Indeed, if you take any two elements e to the I theta with e to the I theta prime, another element, another number, and the theta prime, so that will be same as e to the I theta plus theta prime. Well, theta plus theta prime will be some real number, right? But you can always bring it into this domain by using the fact that e to the 2 pi I is 1, right? So there are two possibilities. Either theta plus theta prime is already in this range. So the two possibilities, one, or it could be that theta plus theta prime is greater than 2 pi. Okay. So maybe it is 2 pi plus some theta double prime, where theta double prime is between 0 and 2 pi. Right? Because anyway, we said that each of these theta and theta prime are in this range, right? So theta plus theta prime can be two possibilities. Either it can be between 0 and 2 pi, or it could be between 2 pi and 4 pi. I mean, less than 4 pi. Correct? So therefore, I can write theta plus theta prime. So this is the second possibility, which is this, where theta double prime is between 0 and 2 pi. In which case, in that case, this guy, I can write it as e to the power of I times 2 pi plus theta double prime. But e to the 2 pi I is 1. So this is nothing else but e to the I. So theta double prime is again in this range, in that range. Okay. So this composition rule gives you again, takes for any two elements here, it again gives you back a third element inside this set, which is done by that. Okay. So usually you just write this e to the I theta as g of theta. I mean, instead of writing an exponential, and the composition rule is g of theta prime is g of theta plus theta prime. This is again a abelian group because the composition rule is just a multiplication. So multiplication is always abelian. And so what are the identity elements here? Identity element is simply theta equal to 0 term. So identity element is nothing else but e to the I0, which is the same as in that notation, is simply g of 0. And inverse element. So what is the inverse of g theta? Well, inverse of g theta is nothing else but g of minus theta. Again, it's understood that this minus, I can always bring it into this range by adding suitable number of 2 pi's. Okay, you can always bring it into this range, like what we did here. You can always bring it in that form. So g of minus theta is actually nothing else but g of 2 pi minus theta. Any questions? So I'll stop for a while to see if you have any questions.
I have one question here, sir. Suppose one element is e to the I pi, and its inverse is e to the minus I pi.
Yeah, which is the same as e to the I pi. Because you can always shift by 2 pi, nothing matters, no? So you're right. I mean, so e to the I pi, so inverse of e to the I pi, inverse of e to the I pi is e to the minus I pi. But this is the same as e to the minus I pi times e to the 2 pi I, right? Because e to the 2 pi I is simply 1.
Yes.
But that's the same as e to the I pi, because 2 pi I minus I pi is I pi. So it's inverse in itself.
Okay. It means that if we apply 2 times e to the I pi, then we will, the vector will be in the same place again.
It will be, so e to the I pi times e to the I pi. E to the I pi, after all, what it is, it's minus 1, right? As a complex number, this is minus 1.
Yes.
So minus 1 times minus 1 is plus 1.
Yes. Thank you.
Yeah, I mean, this, so when I say it like this, if you strictly want to use this range, no, this is how I define it, that the theta should be between this range. Now, in many of these operations, you see, it will go outside this range. For example, even, as I said, even taking the product, it can go outside the range. But you can bring it back into this range by suitably shifting by 2 pi's. No? Because shifting by 2 pi doesn't do anything. You see, if I take e to the I theta and shift it by theta, shift theta by any 2 pi times n, where n is an integer, nothing changes. No? It's the same complex number. This is the same as e to the I theta. So you can use the shift to, by suitably shifting, you can always bring it back to this range. So that's what we did here, e to the I pi. Inverse of it is e to the minus I pi. But what I did, I just shifted it by 2 pi. Right? No? Minus I pi, I shifted to e to plus 2 pi, I brought it back into the same range.
Yes, understood, sir. Thanks.
It's yeah. Yeah. Okay. Anything that, now what I will do is I will, it's in the last 10-15 minutes, 10 minutes. No, today we started a bit late because we had to discuss a little bit, making sure that all the connections were working and so on and so forth. Okay, let me just start yeah. Yeah, I mean, we will see. Okay, now let me start the last few minutes. Slightly more, again, slightly more complicated looking object. So this is actually the beginning of chapter 3. So I'm looking at chapter 3. So here the first section is about group U1, which we already described now. U1 was the one which we just discussed. U1, remember, was the each diameter. 0 and 2 with the ordinary multiplication. Now let's consider another group, which is, I will define it, I mean, the symbol, the meaning of the symbol I will define soon. So SO2R. So what is this? So this is, this is the set of all 2 by 2 matrices with real entries. With the entries are all real numbers. With the entries, with the real entries, not complex numbers, that is. So just real entries. Okay. So in other words, it's like a 2 by 2 matrix where the numbers say A, B, C, D, and the entries are A, B, C, D. So this is a 2 by 2 matrix. Where A, B, C, D are all real numbers. And so that is this 2 means 2 by 2 matrix. R means the entries are real. Okay. What does O mean? O means is an orthogonal matrix. It's not just an arbitrary matrix, but it's orthogonal matrix. Okay. So what does orthogonal mean? So this O means orthogonal. So this matrix has to be orthogonal. In general, if I have a matrix M, then you say that this matrix is orthogonal if M transpose M, the multiplication is just ordinary matrix multiplication, right? And you all are familiar with the matrix multiplication rules. So T means transpose. So you take the transpose of this matrix and then multiply this. And if this happens, this has to be equal to the identity matrix. Okay. This should be equal to 1. I mean, one meaning identity matrix. This is the identity matrix. So, for example, if this was an n by n matrix, M transpose is also n by n matrix. You take the product, and if you say that this matrix M is orthogonal, if M transpose M is equal to identity matrix. Okay. So in particular, now for us is n equal to 2. It's a 2 by 2 matrices. So we are saying this this matrix M must be orthogonal. Okay, that's O. Now, if it is orthogonal, then are you all familiar with this? the matrix multiplications, and yeah, you're all familiar with this, right? Now, you see, if the matrix M is orthogonal, then can one say something about the determinant of this matrix? Well, if you take the determinant of M transpose M, what is that determinant? That determinant, I mean, in general, take any matrix M and take the M transpose and take the determinant of that. Well, you know, these are all square matrices. So determinant, you can factorize the determinant of M transpose. I mean, in general, right? I mean, if I take determinant of A times B, two matrices, which are square matrices, right? Same number of column and row, each of them. Then this is nothing else but determinant of A times determinant of B, right? This is general statement. Need not be for orthogonal. This is general statement. But now let's apply this to the orthogonal matrix. So I take M transpose N, then this determinant of M transpose times determinant of M. But determinant of M transpose is the same as determinant of M, right? Because remember, the determinant, how do you calculate determinant? You open a row, you know, and the cofactors, and you know, this kind of, but it didn't matter whether you open along the row or along the column. Result is the same, right? So here just M transpose is just exchanging row and column, no? So this therefore you see that this is the same as that, which means is determinant of M squared, right? On the other hand, if this matrix is orthogonal, then this is equal to identity by definition of orthogonality. Okay. So on the other hand, if M is orthogonal, then this thing is inside this identity matrix, right? A determinant of identity matrix is 1. Okay, so this is equal to 1. Fine. So we conclude from this, what we're concluding is that if a matrix is orthogonal, then determinant of M square must be equal to 1. Okay, since this is going to be a real number, anyway, so this is a real number. So there are only two possible values it can choose. Determinant of M can be equal to +1 or equal to -1, right? Because this has to be satisfied. So these are the only two possibilities. Okay? Now, when we say S means it's a special orthogonal. S means special. It's called special orthogonal. What S means is that you also put the condition that determinant of M is equal to +1. Okay, so this S means the determinant is equal to +1. Determinant of M is +1. Okay. So if you don't have the S, then you have no restrictions on that. You don't have any restrictions. It could be +1 or -1. So if you just take O2R, it is a bigger set than SO2R. Because here, when I put S, I'm putting a further restriction, right? So this is O2R is bigger set than that. This is contained, this way. This is contained in the O2R. Okay. Now, so we want to check whether this, I mean, yeah. So we want to check whether this satisfies the group properties. Okay. In fact, why am I restricted to 2? I mean, this discussion I can carry for any n. I mean, it doesn't matter. Then I can restrict to n equal to 2. But this discussion we can carry out for any. So you just have n by n matrices, not 2 by 2. So this will be n by n matrices. So you have various n rows and n columns. So n by n matrices. And so that's, now how do we prove that this satisfies all the group properties. So I didn't mention what is the group composition rule. Group composition rule is simply the product of, or did I mention already? I didn't mention that. Huh? The group composition rule is nothing else but the standard matrix multiplication rule. Okay? So if I have M1 and M2, M1 and M2 inside in this ONR or SONR, okay, okay, either ONR or SONR, but let's just work with the ONR for a moment. Okay, so if I have this thing, then M1 times M2 is nothing else but the ordinary multiplication of the matrices. Okay, these are all n by n matrices. The multiplication is all well defined. Because multiplication is well defined only if the the condition, the number of rows of one of them should be equal to the number of columns of the other one. Otherwise, is not right. Multiplication is not defined for the matrix. But here's all square matrices, so multiplication is all well defined. Matrix multiplication, and that's what it is. Now you can ask. So it's ordinary multiplication, ordinary matrix multiplication. Okay. So several questions. First of all, closure. We have to check whether it closes or not. Now, so let us see what we have. So this is orthogonal. So we have the condition is that each of these M1 transpose M1 identity. Similarly, M2 transpose M2 is identity. Okay. Now we want to check if M1 times M2 is also orthogonal, right? This is the main first question we want to ask from the closure property, right? So we have M1 is orthogonal, M2 is orthogonal, and I take the product of these two matrices. The question we are asking is that is a product also orthogonal? If it was not orthogonal, then closure is not satisfied, right? So let's just check. So we are asking the question: is M1 times M2 is it orthogonal? Is M1 and M2 orthogonal? If M1 and M2 are orthogonal. M1 and M2 are orthogonal by definition because I'm taking the elements of orthogonal set, the set of all orthogonal matrices. But this is a non-trivial question. It's not guaranteed, right? So let's check that. So if I take this, to check this, what I have to do, I have to take the transpose of this. When I take the transpose of it, so what is M1 and M2 transpose? When you take the transpose, order changes, right? So this is the same as M2 transpose, M1 transpose. Okay. This you're familiar with it, right? So you do that. Now I want to ask whether this times that is identity or not. But that you immediately see because, I mean, we already said that this is equal to that. So now I want to look at, I'm not sure if you can see this here, all of you. Huh? Can you see if I write here? Better to write there, I suppose, right? I will move it. So let's see. So I look at M1, M2 transpose times M1, M2. Right? We want to check the question mark. The question is it true or not? This is a question. Okay. So first let's apply the property of the transpose. So this is the same as M2 transpose, M1 transpose, and then M1, M2. You see, I am freely moving. I'm not putting any brackets and so on here because we know matrix multiplication is always associative. So it doesn't matter which things you multiply first. Huh? So that's why I'm not putting. If it was not associative, you have to be careful. But this is associative. So, okay. So now let's do this. Now M1 is orthogonal. So M1 transpose times M1 is identity. Right? Therefore, this becomes M2 transpose times M2 transpose times identity times M2. But identity times M2 is M2. That's that. But we also know that M2 is orthogonal. So M2 transpose M2 is also identity. So you see that this is automatically orthogonal. So if M1 is orthogonal and M2 is orthogonal, the product of the two is also orthogonal. So closure is satisfied. Closure is okay. Associativity is all guaranteed because matrix multiplication is associative. Okay. Now the question is about the identity and inverse. So what is identity? So the identity element is simply the identity matrix. Is the n cross n identity matrix. Right? Because by definition, identity matrix times any element m is going to be again m, right? I mean, this is nothing else but 1, 0, 0. Everything else 0. Everything else 0 here. Just the diagonal is 1, 1, 1. I mean, there are n of them here. But we need to check whether, I mean, we need to be sure that this identity is an orthogonal matrix. Identity matrix is not, otherwise it will not even be in the set, right? But that is obviously because a transpose of identity is again identity, and identity times identity. So this is orthogonal. This is also orthogonal. This is the orthogonal matrix. So it is inside the set. Okay. Now finally, the last thing we need to check is what about the inverse? Every element must have an inverse, right? So inverse of n, if n is an orthogonal matrix, is it automatically satisfies this condition, m transpose m equal to identity. So m transpose is the inverse of m, right? Because inverse has that meaning. Inverse times the original matrix should be equal to identity matrix. Identity matrix is the identity element. So inverse of m is nothing else but m transpose, which also exists in the set, because if m is orthogonal, m transpose is also orthogonal. Okay. So all the properties are satisfied of the group. So the conclusion therefore is ONR. So conclusion. So all of this imply that ONR, as defined here, is a group with the usual product rule of the matrices. Now you can ask the question: what happens if you restrict to SO, special SONR? So now the question we are asking is that suppose we restrict to SO NR. Okay. Remember what was S? S, there was just the further restriction, further condition that these matrices must have determinant equal to 1. Okay. Since it is orthogonal, we know the determinant can be either +1 or -1, right? But what this is a restriction. We are saying that we are not going to include those elements here whose determinant is equal to -1. We discard them, we throw them away. Huh? So this is a smaller set than that. Okay? But now we are asking the question, is it also a group under the same composition rule? Okay, which means closure property is satisfied, identity exists, inverse exists, and so on. Well, let's look at the closure property. This is the first question, closure. Closure property, so what we want to check, suppose I have M1 and M2, both are in SONR. Then, first of all, okay, we already know that, so if it is an SONR, of course, it's also an ONR. And we know the product of them is again an orthogonal matrix, right? But now the question we're asking is that, but is the product, the determinant of the product +1 or -1? Okay. Now, so let's do that. Now we want to look at the product M1 times M2, and we are asking the question, what is the determinant of this? But that's the same as determinant of M1 times determinant of M2. But each of them is determinant is +1 because this, by definition, because they belong to SONR. So this determinant is 1, that is 1. So this whole thing is 1. Therefore, we conclude that M1, M2 is also in SONR. Huh? So that's the closure property. And then you can check all the other conditions. That identity, of course, exists. Identity has determinant 1, +1. So it is part of SONR. And the inverse is M transpose. But if determinant of M is +1, determinant of M transpose is also +1, right? So all the conditions satisfied. So this also is a group. It's a group. It satisfies all the properties. In fact, it is a subgroup of that, of this bigger group. Because we are using the same composition rule. Okay. Composition rule was simply multiplication of the matrices. Okay, so maybe I will stop here now. And so this discussion was general for any SONR. But then I will, tomorrow I will specialize it to n equal to 2. Okay, and we'll relate it to the U1. We will see that SO2R is nothing else but the U1. We will see that. I mean, U1 was the one which we defined before, right? E to the I theta, where theta was between 0 and 2 pi, right? That was a U1. And here it's a 2 by 2 matrices, but we will see at the level of group they are the same. Okay? So that will be the topic tomorrow. Okay, any questions now before we stop? So one thing is that there are lots of problems. You must have noticed that in the lecture notes, there are a lot of exercises. No? So what you should do, so there will be a tutorial this Friday. I think there's a tutorial. I think the same time, I think. So you should try to solve the problems. So let's say whatever we do, say until tomorrow, because we need also some time to solve them. So let's say whatever I have done up to tomorrow. Okay, so which will probably I'll finish the 3rd chapter. Yeah, for sure I'll finish the 3rd chapter. Maybe I start the 4th chapter tomorrow. But at least let's say the first 3 chapters, if you can solve the problems and submit it to either Zadeh is going to be the tutor. If you can submit it to her, you have her email address. You don't have the email, okay, then we can provide that email. Anyway, try to submit it by Friday.
To whom we're supposed to submit?
Yeah, sure.
To whom? For whom? So.
For homework?
Yeah, I mean.
Yeah, you can, for those of you who are not here, well, yeah, it will be difficult. I mean, you don't have, do you have the facility to,
I mean, some of us are in the Galileo guest house, so
yeah.
in self-isolation, so
okay.
I don't know, I mean, is it just going to be like, I mean, sent by email or?
Okay, let's forget it this time. I mean, don't submit this week. So we just wait until the whole week. Okay. And submit it next week. All the problems of whatever I cover in the first week.
Okay.
All the exercise of that, you submit the week after. I think that's easier because of this.
So next week, Friday.
Next week, Friday, yeah.
Thank you.
Okay. Any other question?
Do you have any recommendations for other textbooks or something?
Sorry, repeat that again.
Do you have other recommendations for the textbooks other than the lecture notes?
I mean, in this lecture note, there are some references given, but I think you don't need really. I mean, this is pretty self-contained. I don't think you really need anything. There is some reference given, I think, somewhere. I don't have it here. I think in the end of the lecture notes, there is some reference given somewhere, right?
Okay.
That could be, but really you don't need actually. because it's pretty much the things that you will need for the rest of the course, you know, is here. Of course, one can go into very mathematical direction. There's a lot of mathematics in group theory also, but I don't think you'll need that much for the for this course at least.
Okay, thank you.
Okay, so if there are no other questions, then we'll meet tomorrow at the same time, right? 4 o'clock. Good. Stay safe, you know, the dangerous times.
Thank you very much.
Okay.
Thank you.
Thank you,
Yeah.
Professor.
Thank you.
Closed. Yeah, it's okay. Bye bye. Close it. Stop.